In this section, we look at how we can use the normal distribution to approximate the binomial distribution. Now, before we look at the circumstances whereby this can be done, let us look at a simple application. Now, let's take a look at this application. Now, what you see here is a simple histogram that shows you the binomial probabilities when n is 1. Okay, the two bars down there. Okay, you can see that over here, this is when x is 0 and when x is 1. Okay, now notice what happens when I increase n. Can you see that the bars get closer and closer to the red line? And when I increase n, in the end, when n is 100, you can see very nicely the bars fit the bell curve that you see here. Now, what I'm trying to show you is when n is large, the binomial probabilities, right, are very close to the normal probabilities, or I should say, in this case, the normal density curve. So if that's the case, I can use the normal density curve to approximate the probabilities that I need to find for a binomial distribution. Now, we have seen from the application that when n is large, the binomial distribution follows quite closely to a normal distribution. But what are the exact circumstances that are required under the syllabus for you to make that approximation? Okay, now it's all here in this box. Now, let's say I have a binomial distribution with parameters n and p, and our expectation of x is np and variance of x is npq, where q is 1 minus p. Then the circumstances or the conditions that you need is, number one, n is large. And what do you mean by n is large? When n is bigger than 50. Okay, the n bigger than 50 is a yardstick for us to gauge whether something is large or not. Then the additional conditions are your np must be bigger than 5 and your nq must also be bigger than 5. Then you can say that x is approximately normal with mean np and variance npq. Now, before we look at some examples, we need to address one concern first when we make the approximation. Now, I'm going to use a very simple example to illustrate this concern. Now, let's say I've got a binomial distribution, and this binomial distribution has got the parameters 100 for n and half for p. Okay, and then let's say I want to find probability x equals to 10. Now, this probability is easy to find. Just use your GC, and then you can work out the probability. Now, let's say I want to approximate this into a normal distribution. Okay, now let's see whether the conditions are true, will support this. First of all, I need to check whether n is large. Now, n is 100. 100 is definitely bigger than 50, so the first condition is true. Now, the second and the third condition involves np and nq. np is 100 times half, and it is definitely bigger than 5. nq is also 100 times half, and that is also bigger than 5. So the next two conditions are also satisfied. So that means I can say that x is approximately a normal distribution, with mean 50 and variance 50 times half, which is 25. Okay. Now, if I have done the approximation to a normal distribution, then rightfully I am also able to compute this probability. But if you look at this, this is probability x equals to a number 10. Now, we all know that for the normal distribution, okay, is a continuous random variable. And for a continuous random variable, the area under the graph is actually your probability. So if you look at the number 10, the area under the graph is 0 because x equals to 10 is a vertical line. So strictly speaking, if you just make that approximation, then this probability is going to be 0. In fact, it's always going to be 0 for all probability x equal to a single number. So if that's the case, the approximation to a normal distribution is not going to be very helpful. So what people have done, right, to overcome this problem is to change the number 10 into an interval. Okay? Now, what interval am I talking about? Now, let's look at 10 on the number line. Now, what are the numbers that when correct to the nearest whole number will be 10? Okay, this is not too difficult. Any number between 9.5 to 10.5, including 9.5, excluding 10.5, when you correct to the nearest whole number will be 10. So what people have done is, alright, they don't want to look at the number 10. They have changed this to an interval instead. Now, this probability will not be 0. There will be an area. Okay, there will be an area under the graph. Okay, now what I've done is called continuity correction, and this is seen in the next section.